All right. So today we have Federico Carta tell us about non-invertible symmetries in Argyres-Douglas theories. Take it away.
Okay, thank you very much, and thanks for having invited me to give this talk at the Quiver Meeting. It's always nice to be here. I will talk about, as the title says, non-invertible symmetries in Argyres-Douglas theories. Let me just give in one slide an introduction of what is the problem that we tackle and what is our result. So in case anyone wants to decouple completely after this first slide, at least you take at home the message. So in past years, there was a change in the way we think of symmetries in quantum field theory. And in particular, there were many generalizations of the concept of zero-form group-like symmetries, as could be, for example, a flavor symmetries or topological symmetry in 3D equal to 4 theories. And some of these generalizations include higher form symmetries, which are symmetries that act not on point operators, as the zero-form symmetry do instead, but they act on line operators or higher dimensional operators. Or also other generalizations include so-called higher group symmetries, which arise in the case in which there is a non-trivial interplay between zero-form symmetries and higher form symmetries. And then later in the past year and a half, also the concept of non-invertible symmetries was explored in theories defined in dimension greater than 2. And those non-invertible symmetries, one way one could think of them is that the defects that act as symmetry generators, so when they are fused together, they don't produce a single defect, but a linear combination of more of them. And in this sense, like the symmetry operation is not associated to a group-like structure. So with all this generalization of the usual concept of symmetry, a natural question one could ask is how generic are all these symmetries, and which classes of field theories in different dimensions, different amount of supersymmetry, which classes of field theory can admit such symmetries or which cannot. And in particular, in this paper I'm going to present today, we find the result that non-invertible symmetries can be present in quantum field theories of Argyres-Douglas type. This is based on this paper that appeared recently with some amazing co-authors, Simone, Alessandro, and Opadol. Yes, I want to say that this paper is the last of a series of papers I had with the same co-authors, in which we systematically study the presence of all these type of symmetries, higher form, higher groups, and finally non-invertible, still in this class of Argyres-Douglas theories, which we like especially.
Federico?
So, sorry?
Yeah, these symmetries that you find, can they be used for doing some representation theory to identify some spectra and representations of the different observables that we did not know before?
For non-invertible symmetries, I don't know the status of this. And for higher group, I am aware of a recent paper of Matthew Bullimore and collaborators in which he exactly studies representation theory of these symmetries. But I've not had time to read that paper, so I cannot comment.
I see. So the question will be if one can get a new form of the spectrum, some understanding we didn't know before, as a result of the presence of such a symmetry.
Yes, I guess that could be possible, but I also don't know what is the status of the representation theory of these higher symmetries.
Okay, thank you.
You're welcome. So let me give the plan of the talk. So I will start with an introduction, review of Argyres-Douglas theories and what they are. And this part might be maybe boring for some people in the audience, but I hope that maybe it could be useful for younger people or people that are not familiar with these theories. And I will discuss one way to generate a vast amount of Argyres-Douglas theories, which is geometric engineering of type 2B superstring theory on some isolated singularity. Later, I will focus on a specific family of Argyres-Douglas theories, which are the so-called DPG theories. I will discuss some of their properties, and more importantly, I will discuss a setup in which we have a bunch of DPG theories, each one with its own flavor symmetry, and we just gauge the common diagonal flavor symmetry of all of them, making some kind of like quiver-like object where we have a weakly coupled vector that is gauging many non-Lagrangian sectors. This theory we construct in this way is the one for which we want to argue that there are non-invertible symmetries. It's not just a theory, it's an infinite family. We will see that later. At this point, I will change completely topic in some sense, and I will discuss non-invertible symmetries. I will review non-invertible symmetries in the case of 4D n equal to 4 Superyan-Mills theory, which is theory completely different from Argyres-Douglas, a double amount of supersymmetry. But nevertheless, we will see that this family of Argyres-Douglas theory that we will study shares many similarity with the n equal to 4 theory. And in particular, what we would like to do is to apply the known way to construct a non-invertible symmetries n equal to 4 theory to those Argyres-Douglas theories. In order to do that, we need to understand better what is the conformal manifold for the Argyres-Douglas theories, and in particular how the S-duality acts on them. And now there are two different cases. One is the one in which some of those Argyres-Douglas theories admit some classes description as well on top of the geometric engineering. And the other construction is when we can find them as a compactification of 6D n equal to 1 theories on a torus. So this is the plan of the talk. Let me start with the introduction of Argyres-Douglas theories in general. So Argyres-Douglas theories are 4D n equal to 2 superconformal field theories, which were originally found in the 90s at very special points on Coulomb branch of some asymptotically free n equal to 2 gauge theories. So the first example historically, and also the easiest one to understand, is the one of pure SU3 Superyan-Mills. So if we consider pure SU3 Superyan-Mills theory, this theory is rank 2. So the Coulomb branch is 2-dimensional, and the lattice of electromagnetic charges that BPS particle can have is 4-dimensional. We have 2 electric and 2 magnetic charges. And now, if we consider the pure SU3 theory in its Coulomb branch, there could exist BPS particles with a given electric and magnetic charges, and if they exist, their mass is given by the absolute value of the central charge, which takes this expression depending on the electric and magnetic charges, and also coordinates parameterizing Coulomb branch A and A dual. Now, the A and A dual are explicit functions of the semi-classical Coulomb branch coordinates, and the explicit dependence of A and A dual on the semi-classical coordinate is known due to Seiberg-Witten theory. So this means that a given BPS particle of electric and magnetic charges will have a mass that depends explicitly on the point in which we are in the Coulomb branch. If we are at a different point, the mass will be different. And in particular, can happen that at some points, the mass of a given BPS particle just becomes zero. It's a possibility. There will be, in general, a full codimension 1 locus in which a BPS particle of given electric and magnetic charges will be massless. And can happen that even more than one BPS particle becomes massless at the same point. Now, there are two possibilities. One possibility is when two different BPS particles become massless at the same point, but they are mutually local. And in this case, it's possible to use an S-duality transformation of the theory in order to go in a S-duality frame in which only one of these particles is massless. However, in the most interesting case, when more than one BPS particle become massless at a given point, and they are also mutually non-local, it's impossible to find such a S-duality frame. So when this happens, the low energy effective field theory at that point is some vector multiplet interacting with those particles, but it's impossible to write a Lagrangian for this theory, especially exactly because like we have mutually non-local particles becoming massless. So in this particular example of the SU3 theory, this was studied in the 90s, and we call this theory H0 or also A1, A2. And this is in some sense the simplest for the n equal to 2 superconformal field theory, in the sense that the central charges are the lowest of all theories, excluding the free theory. Now, one important feature of Argyres-Douglas theories is that Coulomb branch operators have a fractional scaling dimension. So the eigenvalue under the dilatation operator of the Coulomb branch operator is generically not integer. And this is another reason for which they cannot have a Lagrangian description. And another interesting feature of these theories is that the number of degrees of freedom scales linearly in N. So, for example, if I compare the Argyres-Douglas theories that I can find in the Coulomb branch of pure SUN, and I let N increase, I will see that the central charges increase linearly. And this behavior is completely different from ordinary gauge theory, where the degrees of freedom scale quadratically. Okay, so very good. Now let me move to one way to construct a vast amount of Argyres-Douglas theories. There are various constructions for this family of theories, and were developed in the years. A large one, but not exhaustive, in the sense that not all the Argyres-Douglas theories admit this description. But a large one can be obtained by compactifying type 2B string theory on a singular Calabi-Yau threefold. So this setup, the Calabi-Yau threefold can be some hypersurface singularity. So, for example, a single equation in C4, the zero locus of some polynomial in C4 will give me a threefold. But it doesn't need to be limited to this. Like you can have, for example, more than one hypersurface and some complete intersection, or you can have, and we will have later in the talk, case where the polynomial equation is not defined in C4, but C3 times C star, for example. Or in general, one can also think of more complicated ambient spaces and so on. So just to give an example, when we take this polynomial in C4 to be given by the sum of two AD singularities, then this setup will engineer so-called GG prime family of Argyres-Douglas theories. In a specific example, we can take this polynomial here, x1 squared, x2 to n plus 1, x3 squared, x4 to n plus 1. And this realizes some theory that is called AN, AM, which is just a generalization of the A1, A2 theory that we saw before, the one found in the 90s. Very good. So this is just an example of the geometric engineering. And now one could think, okay, for any polynomial that I can think of, any homogeneous polynomial, I will define a superconformal field theory. And this is false. There are some constraint. So in particular, we would like the singularity is isolated, which means that should be a single solution to the equation set to 0 and also to the gradient set to 0 at some values of the coordinate, which we can usually take at 0 if we parameterize in a nice way. This is one condition, and it's important that the singularity is isolated, because would it not be isolated, I would not engineer four-dimensional theory, but rather something that is like a system, a coupled system of a 6D theory and the 4D one, in case I have a non-isolated singularity. The second condition that we need to ask when we do this type of construction is that the singularity is at finite distance in modular space. And the reason for this is that when we have a singularity at finite distance in modular space, we typically have a finite number of degrees of freedom that are massless at the singular point, while when the singularity is at infinite distance, we typically have entire infinite towers of state that become massless. For this class of theories, the condition for the singularity to be at finite distance is easy to check, because one can think of this type of models from the point of view of the worldsheet of the type 2B string. And from the worldsheet point of view, this is some Landau-Ginzburg model that has a C-hat central charge that depends explicitly on the scalings of the coordinates of the equation that defines the Calabi-Yau, that in this point of view is the superpotential of the Landau-Ginzburg model. And so as long as this is smaller than 2, the singularity will be at finite distance. Okay, so this restricts a bit the possibilities that we can have to do geometric engineering. But what we want to do and want to discuss in this talk is the case in which we actually do something a bit different, and we replace one of the coordinates, like x4, for example, with the e to the x4. So we actually consider an equation that is in C3 times C star instead of C4. So this will engineer a different class of geometries compared to what I was discussing a bit ago. And among this class of geometries that are given by single equation in C times C star, we will engineer some Argyres-Douglas theories that are called DPG, which will be the main, one of the main characters in this talk. I will not go in details of which equation engineers which DPG, or what is the relationship between these DPGs and the GG prime theories I had before. But the point is that there is a way to do geometric engineering and get this type of theories. Now, let me say immediately one important feature of these theories. They have at least a flavor symmetry group G, where at least means that they always have G, but sometimes there are also some P and G. Good. And now, what we want...
Federico, can I ask a
Yes.
When you said finite distance in moduli space, can you remind me what is this moduli space? And
For example, complex structure moduli space. So you have the equation when it's just like, let's make an example, just like this, set to 0. Then you're at the singular point, but you can add the deformation that are subleading monomials depending on some coordinates, and the coordinates will parameterize complex structure moduli space. And now you can pick a generic point in complex structure moduli space.
Okay, so you want to be at finite distance from a generic point.
Yeah, you pick a generic point and you compute the distance by using the metric on the complex structure moduli space from this point to the origin, or where the singularity is, if you parameterize well, is always in the origin. And this distance should be finite.
Okay, thank you.
Okay, good. Yeah, for example, if you want to look at this type of computation, when you set n equal to 1 and m equal to 1, this is the conifold. And this computation has been done by Strominger in the 90s in a very famous paper, which he was studying essentially the conifold transition. Okay, so where were we? Yeah, so this DPG theories have at least a flavor symmetry group G. And this is important for what we want to do, because what we want to study is not the DPG theory itself, but is a theory that is constructed in the following way. We take a bunch of these DPG theories and we gauge the common flavor symmetry. So we want to make this type of quiver-like object, if you want. Now, we cannot take an arbitrary number of DPG theories or arbitrary choices of P if we want to save conformality, if we want to make a conformal theory after the gauging. However, the weight that the non-Lagrangian matter has on the vector that we are using to gauge is known, because we know what is the flavor central charge for these theories, can be computed in many ways. And so in particular, one finds that if we want to gauge in a conformal way, n equal to 2 gauging here, a bunch of DPG theories, there should be this condition satisfied here, where this condition comes essentially from equating the sum of all the flavor charges, which is the weight of the matter on the beta function coefficient, to the weight of the vector on the beta function coefficient. And the matter and vector always have opposite weights. So when there is some kind of balancing condition, the theories you obtain will be conformal, and there are not so many possibilities. So we can only have families of this type. 3 of them are like trinions, where we have a vector that is interacting with 3 matrix sectors. And one is, let me call it quadrinion, where one vector is interacting with 4 different matrix sectors. Okay, very good. Now, from now on, I will specialize on G equal to SUN. And for the moment, let me restrict also just on these trinions theories. So for these trinions theories, it happens that not only the DPG part, but the full trinion itself admits some geometric engineering description of the following type. This was studied extensively in these 2 very nice papers of some years ago for all theories of these types and even more general ones. Good. So let me comment on this point here, and this is related to what Antoine was telling before. So the deformation of these geometries correspond to operators or waves of operators that parameterize the extended Coulomb branch. So in particular, if I have just this part, we are at the superconformal point, but if you add the deformation, then the coefficients of this deformation will be either wave of Coulomb branch operators, masses, or couplings for this theory. And what is important and will be important in this discussion is that despite the fact that these theories are not, like non-Lagrangian, they are not isolated. So you can have marginal couplings, and indeed you will have marginal couplings for the vector that is weakly gauging. So in this geometric description, this coefficient here, one can compute the dimension of this, and you can see that this is dimension 0. So this is where the marginal coupling is entering in the geometry. Okay, so this is an important point. Now, another comment is that from the type 2B engineering is usually not so easy to understand the topology of the conformal manifold. It's easy to understand, to count the marginal operators, but not easy to understand the various weakly coupled cusps or how S-duality acts in general. Are there questions at this point? Seems no. So let me go on. So this is essentially the family of Argyres-Douglas theories we want to argue that they admit non-invertible symmetries. Now let me change completely topic and let me move to how you construct non-invertible symmetries in n = 4 theory. So for the n = 4 Super-Mills theory, let's take Lie algebra SU2 to make it simpler. So this is not a unique theory. It comes in 3 different variants depending on the global choice for the global structure of the gauge group. So one can have gauge group SU2, gauge group SO3 plus or SO3 minus, where here the plus and minus is related to the fact that if we consider the set of line operators for this theory and this theory, they will be different. Or equivalently, the theta angle here and here will be shifted by 2 pi. The 3 variants are related by elements of the S-duality group, which is SL2Z in this case. So in particular, if you start with SU2 theory and you act with S, you do change the global structure of the gauge group. So you are mapped to a different theory. Now, this type of situation gets complicated a bit if on top of considering the possible action of S and T, we also do introduce other 2 operations, which are the following. So first one is gauging the one-form symmetry of this theory. So the SU2 theory has a Z2 one-form symmetry coming from the center of the SU2. And this symmetry can be gauged. Gauging the one-form symmetry also does change the global structure of the gauge group. And the other operation would be considering the background gauge field for the one-form symmetry, so a 2-form field, and adding to the action a term that is essentially a square of this background field. It's a Pontryagin square. Okay, so there is this map of operation that connect the various theories. Here, the subscript 0 or 1 just means that the fact that this term is included or not, and the plus and minus is the same meaning as the slide of before. And what is important for us is are closed loops in this type of diagram, because for every closed loop, we can define a non-invertible symmetry. In particular, I want to focus on this closed loop, which is the simplest one. So the idea is that if I start with SU2, and then I act with sigma, so I gauge one-form symmetry, and then I act with S, I go back to the same theory. Okay, so this is what it was used in this series of papers this year and last year and 2 years ago to construct the non-invertible symmetries. In particular, this is what I was saying before. You start with SU2 at without that extra counter term that I was saying before, and we want to do operation of sigma and S This will map me back to the same theory. However, the coupling is flipped because sigma doesn't do anything to the coupling, but S acts both on the coupling and also in changing the global form of the theory. One way to think of these two operations is think of them separately, like even separately in space-time. So I can think space-time R4 to be like R3 times R, and I can think that for coordinates smaller than some amount in this R direction, I have the SU2 theory, and then at some point I act with S, so I change the global form of the gauge theory, and then further away in space-time I act with S, and so I am back with SU2 at coupling -1 over tau. And one could consider the limit in which you make these two operations the same space-time point, and this is the situation I was discussing before. Now, if we are at a generic value of tau in this setup, or also in this setup here, we will have some like domain wall separating these theories, some interface. However, if we go at tau equal to I, then the theory I have on the left is literally the same theory I have on the right. So interpretation of this interface is not like a domain wall between different theories, is more like some surface operator that belongs to a same theory, which is SU2 at tau equal to I in this case. So this is the way non-invertible defects were constructed in this series of paper here. The claim is that at tau equal to I, this interface becomes generator for some non-invertible symmetry. This claim is supported in the papers here by more details, as for example, computing explicitly the fusion rule when one of the defect of this type is attached to a defect of another type. I will not go in all of this. So what I need for this talk is simply the fact that in order to do this construction, we need two things. We need a one-form symmetry that we want to gauge, and we need some S-duality. And this S-duality has to do two things for us. It has to change the global structure of the gauge group, essentially to compensate what the gauging of the one-form symmetry did. And also, it should be such that at some point in the conformal manifold, the coupling is left unchanged. So those are the two things we want to look for in our DPG trinions. Because if we do have those properties, then we are in good shape to argue or expect that this exact construction can be ported to the Argyres-Douglas theories as well. Questions at this point? Seems no, so let me continue. So we want to study the conformal manifold of these theories. Let me first study the case of the quadrinion, where I have 4 different DPG sectors. So for these cases, let's split the discussion in 2 subcases as well, depending on if the gauge group is SU odd or SU even. Let's do SU odd first. So I have 4 D2 SU 2n+1 matrix sectors gauged together by an SU 2n+1 vector. And luckily, it turns out that this theory also admits a class S description without the need of irregular punctures. So we can find this theory inside the class S of type A2n. And A2n admits some outer automorphism, so it makes sense to consider twisted punctures in this case. And the description is a sphere with 4 minimal twisted punctures. Now, of course, 3 of the punctures we can put at 0, 1 at infinity, as usual. And the other puncture is essentially free to be wherever it wants, and we can parameterize this position as Q. The position of this puncture is parameterized in the conformal manifold of my theory, which is one-dimensional as it should, because I have one vector that is gauging the four matter sectors. And now we want to study a conformal manifold, and conformal manifold is quite visible in class S, and the weakly coupled cusps arise in limits in which one puncture collides with the other. So, for example, when Q collides 0, the tube becomes very long and very thin, and eventually the two spheres separate. And this is a weakly coupled limit. You can think of Q to be like a function of tau, essentially. Now, yes, so when Q goes to 0, the two spheres separate, and each one would carry like the two twisted punctures plus a maximal puncture, and each one of these two spheres by itself would engineer two copies of the D2 theories. Good. Now, by the way, here, since the punctures are twisted, they are connected by a Z2 twist line, okay, which is the meaning of this dashed line here. Now, this setup is very similar to a simpler setup, which is the one of SU2 with 4 flavors, where we also have 4 punctures, but they are all untwisted. And in that case, for SU2 with 4 flavors, we know that there is some SL2Z S-duality. So we would like to argue the same for this case. So in order for this to happen, the various weakly coupled cusps should be equivalent to each other. And one way to study this is the following. So we understand what happens when Q goes to 0, but what is the case when you have a different collision, like Q goes to infinity? So let me now show the picture of Q goes to infinity. And please notice in this new picture, the twist lines are exactly where they were. So from 0 to Q and from 1 to infinity. So 1 to infinity and 0 to Q. I've not moved the twist line. I'm just trying to go in the different cusp in the conformal manifold, which is the one in which Q goes to infinity. So when Q goes to infinity, the tube becomes very, very thin, very long, and when it's too thin, the twist line is essentially collapsed one to each other just because the tube is so thin. And they are two twist lines, each one of a Z2 twist. So the collision of two of them would be like a trivial line. And so essentially in this limit, when Q goes to infinity, you can rearrange the twist lines like this. So the limit of Q going to infinity, essentially collapsing these two punctures and the twist line between of them, is the same as the limit of Q going to 0, collapsing two puncture and twist line between them. So this is nice because it's telling us that the various cusps look the same. And also it's nice because the limit Q goes to 0 is a cusp that is S-dual to the one of Q goes to infinity. Again, remembering to think of tau as a function of t. Now, we would like to understand how the S-duality acts on the global form of the theory. Because in the Sperry-Mills case, S-duality was changing SU2 from SO to SO3 plus. And now, in this case, it's understood that the defect group of the theory is Z2n plus 1 squared. So you can think Z2n plus 1 electric one form and the other like magnetic one form. And it's generated by two cycles. So one is like going around two punctures on the twist line, and the other is passing through the two twist lines and separating punctures in this way. You can even think, if you want, as this these things as a Wilson and Toft line for the 4D theory, coming from, for example, a surface in 6D, that is wrapping this circle or this circle. So one dimension of the surface is wrapped, and in 4D I have a line. Now, if we take this setup and let's assume that when Q goes to 0, I was in the global form of SU2, to n plus 1. Then if I do the other degeneration limit and I rearrange the twist lines as I showed before, I see that they get flipped. So who was the Wilson line becomes the Toft line and vice versa. So if for Q equal to 0, SU 2n plus 1 was the group that was getting weakly coupled, for Q goes to infinity, that is the cusp that is S duality related to this one, it's a PSU 2n plus 1 that is getting weakly coupled. So then this is literally the same situation of n equal to Fuchs-Pinnian-Mills. Very good. So this is the discussion for the quadrinion theory with the central group SU 2n plus 1. Let now me say the case of a central group SU2n. This is very analog in spirit, just a bit more complicated. And so just because a class S description has more punctures. So what happens here is that this D2 SU2n, despite looking Argyres-Douglas type, it's actually a Lagrangian theory. It's actually like SU2n with double amount of flavors. So sorry, SUN with the 2n flavors. So essentially, when you have 4 copies of this and you gauge them, this is just like a completely Lagrangian theory. It's a quiver of 4 SU n nodes, and at the center I have SU 2n node. So it's like the affine D4 quiver. Now, in this case, since I have a 5 gauge group, the conformal manifold is 5-dimensional, not 1-dimensional anymore. And the classes description is in classes of A to n minus 1 type. And I have 4 twisted punctures, but also 4 untwisted punctures. And here again, we can put 3 at 0, 1, infinity. And the ones that are free to move are 1, 2, 3, 4, 5, just as they should, because I have 5 marginal couplings. We can replay exactly the same argument of before, of the different cusps with Q to 0 or Q to infinity, and Wilson and Toft line rearrange and so on. Everything goes the same, but there is the complication of this other extra puncture. So what we need to do is that when we take this degeneration limits, we should do it in a way that does not interfere with the position of the other punctures. So what we say is that we don't understand the full conformal manifold here, but we do understand that within the full conformal manifold, there is a 1-dimensional conformal manifold, a 1-dimensional submanifold, which is the one parameterized by Q. And for the cusps lying in this conformal manifold, we still have a structure like the one of the other quadrinions we considered before. So we still have some SL2Z, and the S is changing the form of the global group. Questions for now?
I was just wondering, can you map this Q? Well, let's say in the previous example, which is simpler, can you map the Q to the alpha parameter you had before in the geometric engineering?
Well, so this geometric engineering was for the case of 3 matter sectors. While here I'm considering case of 4 matter
Ah,
sectors.
yeah. Okay.
But wait, because we will map
later you
alpha to something else in the next slides. Okay.
Okay, I see. Thank
Okay. So here I'm discussing the case of 4 matter sectors. This one.
Mhm.
Okay. I've not talked about this tree because for this tree we cannot use class S, sadly, but we can do something anyways, and we will. So what we want to argue is the fact that there is a cell to Z also in these cases, and we do that by considering these theories arising from 1,0 compactification on a torus.
Mhm.
But let me say something before going to that. So let's recap this part of the discussion, the class S discussion. So we have seen that for the case where we had like a to n minus 1 with the 4 twisted puncture, we have this z to n, and then this thing that when q goes to 0, some SU to n gets weakly coupled, and when q goes to infinity, some SU to n mod Zn gets weakly coupled. This is a tiny bit different than the superior Mills case because it's not SU to n mod Z to n, so it's not P SU to n, but still is a different global form than the one you had in the other S-duality frame. So to recap, at least for the reagents with 4 copies of DPG, everything goes more or less similarly to the n equal to 4. So we expect that the same type of non-invertible defects should exist. Now let's go to the cases of 3 copies. So the trinions, and this is what I was saying before. We need to change description. We cannot use class S anymore. We use 6D 1,0 on the torus. And what we would like to get in the end is the fact that the marginal coupling of the 4D theory is equal to the modular parameter of the torus. And so we would like to use this type of description to argue that there should also be an SL2Z S-duality for these theories. Let's first discuss what is the 6D theory we use, and we consider compactification of F theory and some elliptically fibered threefold, and we take geometries of the form C2 times C2 times gamma, mod gamma. So gamma is some zk times zn that acts in this way. So here the first 2 coordinates are for C2, the last coordinate is for T2, and k cannot take any value essentially because there are, in order to make the zk action behave well on the torus, k can only take some values. And there are 2 cases, 2 different cases depending on k and n, and this depends on essentially if they have if they are coprime or not. So if they are coprime, then you can repackage zk times zn in zp, and you can consider this type of action of zp. And then when and the type of theories that are engineered in this way, one comment is that they are also always non-xable, so they will be theories without X branch in 6D. When n instead is a multiple of k, we find G, G conformal matter, and depending on the value of k, we have a different G. Like for example, you have like E6, D4, E6, E7, E8 for the various values of k. For both these theories, like the one of the first type with Kn and coprime, and the other one, the defect group is known. So here we are in 6D, so the defect group is encoding, for example, a 2-form symmetry of these theories. And then in the case that it's coprime, this is Z and K. In the case in which one is multiple to another is Z n over K's for K equal to 3 and 2n over K's otherwise. So anyways, like without tons of details, the fact is that we know the two-form symmetry in 6D, and the one-form symmetry in 4D will be some subgroup of the two-form symmetry in 6D. But okay, so this at the moment I've just declared that this is a description of some 6D theory. I want to check that my DPG trinions actually come from the reduction of this 6D theory on a torus, no? So that the two things are connected. Well, so we want to put these 6D theories in T2 and argue that we find our DPG trinions. There is a complication here, and the complication is that when we do this chain of duality, F theory on Calabi-Yau threefold times T2, this is the same as type 2A on Calabi-Yau threefold, and this is actually getting me in general some Kaluza-Klein theory. One way to see that is that if let's do like step by step, I have F theory on Calabi-Yau 3 times T2. Let me go down one circle, then I have M theory times Calabi-Yau 3, M theory on Calabi-Yau 3 times S1. We know M theory on Calabi-Yau 3 give me if Fn equal to 1 and CFT, but if I go down an S1, in principle, I need to take care of the Kaluza-Klein modes, right? So that is one difficulty that we have. Anyways, let's follow the duality. So we have F theory on Calabi-Yau 3 times T2, go down to type 2A on Calabi-Yau 3, and then we can consider type 2B on the mirror of Calabi-Yau 3. And now here we are back in the setup that we like to be, the geometric engineering of type 2B on a Calabi-Yau threefold, but it's the mirror of the one I was describing before. So it's the mirror of this orbifold. Well, okay. So as I was saying, in general, when I consider type 2B on these mirror geometries, I will have a Kaluza-Klein theory. For the cases that are conformal matter, it's understood that we will have a Kaluza-Klein theory. For the other case, we really don't know. We don't understand what this Kaluza-Klein theory is. Anyways, what we would like to argue is that within all the modes of this theory, that can be 4D modes or Kaluza-Klein modes, within all of this, there should be the DPG trinion. And so actually, when we consider geometric engineering of type 2B on the mirror of the orbifold, we know what is the description of the mirror, and again is some Landau-Ginzburg model with the superpotential of this form. And what you see remarkably is that you have one part of the superpotential, so one part of the equation defining this Calabi-Yau, that is exactly what was the known geometric engineering of the trinion that I showed before, the one for which Antoine was asking if alpha could be related to something. And yes, now alpha can be related to tau. So like if you follow this chain of duality, you will find that what was the marginal parameter alpha that we had slides ago, it's exactly the complex structure of the torus that we have when we do this, well, don't do this one, the one with the compactification. Okay, so essentially what we'd like to do is find some tuning of the terms that we have in this side, and some tunings, so going to special points in complex structure modular space and change of variables, such that in the end we remain with the part that engineers the trinion. I will not go in details of this change of the tuning and the change of variable thing, but essentially the message is that we think all of this is engineering in some Kaluza-Klein theory that has lots of Kaluza-Klein modes, but out of this you can still extract a part that is giving you exactly the geometric engineering that you expect for the CFT. Point one. Point two, the complex structure of the torus that you have when you do this compactification shows up in the geometric engineering exactly where the marginal coupling of the Fourier theory should show up. Okay. So essentially, let me conclude. We have constructed some families of Argyres-Douglas theory. Some are this trinion, some is the quadrinion, and with one way or another, like either classes with twisted punctures or the 1,0 compactification and the F theory setup, we always seem to find that for this family of theories, there is some SL2Z duality group. Also, there is one form symmetry, and the operation of gauging one form or adding the counter terms are exactly the same as the n=4 thing. So it seems literally that all the necessary ingredients for having the non-invertible symmetries are present in this case. So we would like to argue for the presence of non-invertible symmetries also in these families of Argyres-Douglas theories. Last comment. So in the case in which a conformal manifold was dimension 1, it's a fact that central charges are equal for this quadrinion here, and so here, or also the trinions, and this is a very similar thing to the n=4 superior Mills setup, where central charges are equal. But we also seem to find that in the other case, in the one in which a conformal manifold is higher dimensional than 1, also in that case there is the SL2Z and there are all the right ingredients, but this is somehow starting to be a bit different than superior Mills, at least from this point of view. Okay, so I think I said what I wanted to say. Let me give a final remarks or conclude. So we have seen that DP SU trinion or quadrinions behave similarly to for n=4. They have same duality group, and actually, independently from our reasoning, this type of connection was confirmed by partition function index computation by other people. So, for example, one can take the index for a very simple member of these families of trinions and do just a change of variable in one of the fugacities entering in the index and recover the n=4 index, essentially. So there are many similarities also identified in different ways. And there are also interesting directions. So, for example, our way to argue for the S-duality is not extremely direct, I would say. So, for example, we don't understand exactly how this acts on the parameters. And we would like to see this more explicitly. Of course, we can try to generalize this by taking dpg with G given by D or E. There is also a notion of dpg for non-simply laced G. There are also more generic theories than dpg that are so it's possible maybe that something generalizes along these lines. One thing I did not write, but would be interesting for me, is understand better the non-invertible defect itself. Asking, for example, if the theory if the topological theory that you need to stack to the defect to make it gauge invariant is the same as the n=4 case or not. And of course, you can generalize, for example, by studying n=1 gaugings of DPG theory, as was done recently by Craig, Monica, and co-authors. So yeah, there are many things that could be done, in my opinion. Thank you very much for attention.
Okay, let's thank Federico. We have questions.
Maybe I can ask, but that's what you said, I think, at the end. But so you show indication that there is this non-invertible defect, but you cannot. Can you really prove that it is non-invertible? Like, do you say that the fusion rules will be the same as in n = 4, or could it be invertible? Like, could you imagine a way where you have your gauging of one form symmetry and also your duality, and still the defect is invertible? I don't know if
no, I don't think it's like this, because something I did not mention, because I did not want to enter in all of that. But so the way you have, so the general way in which you construct these non-invertible defects, even more general than equal to 4, but as a principle, you want to have a 0 form and a 1 form symmetry, and you want to have a mixed Taft anomaly between them, and then you want to gauge a 1 form symmetry. So if you do that naively, you would say, okay, I gauge the 1 form symmetry, then the 0 form is broken. But actually, this is not broken if you take the defect that would implement the 0 form symmetry. Now this is not gauging variant, and then you stack on top of this some topological field theory. So this is one way to see this. And in our setup, we still have this fact that there is the mixed Taft anomaly. So I do expect that at this moment in which I gauge the 1 form, it already cannot be invertible, this thing. So I already have to do this operation.
You know that you have the mixed Taft anomaly.
Yeah. We know that we have the mixed Taft anomaly, and that, to my understanding, is enough to say that this thing will be non-invertible. But if you start asking about the fusion rules and all of that, I don't know. We did not do the computation, at least I didn't for sure.
Okay, thank you. And actually, I had another question about the moment you had the SU even theory, the one with the 8 punctures.
Mm-hmm.
So in principle, you made this argument with the different S-duality frames, but in principle, you could have the Q puncture going around another of the punctures. Say you take Q close to 0, then you move it and you go around one of the other punctures and you go back to 0. So now the twist line goes around the puncture. And do you know how this affects the theory? Like, do you have an action due to this, some monodromy around the other punctures?
Okay, so you wanted to go from Q to 0, but encircling one of the untwisted
so now the twist line goes around the puncture, and I'm not sure it can cross it. So it's just to understand if it's well defined, like all these duality frames, in this case where you have many more punctures, it's not clear to me that this still makes sense.
I think maybe this is related to what I was trying to say before, that we want to go from Q to 0 without the interference of the other punctures.
Sure. Yeah. So I understand that there's one frame in which it makes sense, but are there other versions of the theory?
I don't know if it's a frame. I think of it as some submanifold of the conformal manifold. So for all the possible ways I can go from Q to 0, I choose to make a path that
okay, if you choose one, I don't doubt that this is correct, of course, but I was wondering if there are other, like if you precisely don't do this and you take another path, do you reach something different or not? Or maybe, I don't know if it's no. I was just curious.
Yeah, I don't know the answer to this question.
I was just curious.
Probably this looping around has to do with key transformation.
Mm-hmm. Okay, so in certain frames it would change and in others it would not, these kind of things.
Mm-hmm.
Yeah.
Well, yeah, untwisted punctures, I think, can, they can go across twist lines. They do not care.
Okay. So then it's all good. So actually, there is no real interference with these other punctures.
No.
Okay.
But as long as you always focus on specific degeneration limits, if you start moving the untwisted punctures around, then yeah, you're leaving from the nice one-dimensional submanifold.
Very nice. Do we have more questions? It was really a very clear talk, so it's
Yeah.
And then Antoine asked the easy question.
Yeah, I'm the only one, not understanding
I
anything.
don't.
So that's why I asked.
I don't have.
All the others, it's
Yeah.
all clear.
No, but let's say the obvious question. But okay. Yeah. Well, speak now if you have more questions.
I had a question. So you said that there is a mixed tooth anomaly between 0 and 1 form symmetry. So does this mean these symmetries you found and non-invertible symmetries are intrinsic here? Or are there like non-intrinsically non-invertible symmetries? Do you know if you investigated that?
I always don't remember the nomenclature between intrinsic and non-intrinsic. So the Kaidi-Omori type of non-invertible, is it called intrinsic or non-intrinsic?
So they had both types. They had this equation where they acted with these with the S and T dualities they labeled these different global structures by different matrices of in the class S by SP to Zn maybe, and then they acted with S and L duality, and if there were no eigenvalues, they said it was non-intrinsically non-invertible. And yeah, if you don't remember, no worries.
Yeah, I don't.
Thank you. Anyway.
May I answer this question, please? We have both. So a simplest example would be take SU2 in the middle with the D3 SU2, 3 copies, you get A2D4 theory. In this case, you can show that they admit 3 global forms. So SU2, SO3 plus, SO3 minus. In one frame, if you look at S, you can obtain something called non-intrinsic because this is a mixed anomaly by Kaidi-Omori. You can also look at ST. This is element of order 3. Then it's parallel to n equal to 4 SU2 gauge algebra that you can also have the triality defect, which is non-invertible. And this is non-intrinsic, I think.
I see, thank you.
Any more questions? Okay, well, I'd say let's thank Federico again.
Thank you.
This was very nice.